start by thanking the organizer for putting our paper onto the program and giving us the opportunity to present our work. This paper is a joint work with Hitachi Doshi and Chris Jacobs, who are also joining us today. In this paper, we studied the modeling of volatility process in dynamic term structure models for treasury yields. So in affine term structure models, simultaneously matching conditional means and variance of yields remains a key empirical challenge. There is considerable evidence in the literature showing that volatility implied by these models corresponds poorly to the measures of realized volatility or other model-free estimates, such as gauge estimates. It has been shown that the trade-off is partly because the mean and the variance of yields are driven by the levels of the same state variables in these models. In this paper, we propose a class of non-arbitrage affine term structure models in which the volatility factor follow gauge process. This model provides an analytical solution to bond price and bond yields. And in this paper, we investigate the model's ability to capture the time series and cross-sectional properties of the yield volatility. This is motivated by the well-established arch and gauge literature. There is ample evidence showing that arch and gauge models can provide an adequate characterization of the interest rate volatility. So therefore, in this paper, we incorporate a gauge volatility into the affine term structure models. Our paper, of course, is not the first one tried to build gauge volatility into non-arbitrage model. Our model is built on Heston and Nandy 2003, but we propose a more general framework that allow us to analyze the modeling of the yield volatility and also the model's potential to resolve the tension between modeling yield level and yield volatilities. We relate the conditional volatility to the lagged squared residues of the factors driving the yields. This is the key difference from the modeling perspective from the standard affine term structure models with a stochastic volatility, in which volatility is specified as a linear function of the level of the yield factors. In this paper, we use a three-factor model, a standard model, but in order to model the volatility, for simplicity, we only let the volatility of the residues of the first factor to follow a gauge dynamic. And we refer this model as non-arbitrage gauge model through this paper. We compare the performance of the proposed model to that of the benchmark models. The main benchmark model considered in this paper is the widely used essentially affine model, A13 model, with one factor driving the volatility process as specified in Dye and Singleton. And to facilitate a comparison to our proposed model, we also consider a restricted version of the canonical model, under which the dynamics of the yield factor is exactly the same as our proposed model. So in both canonical and restricted model, the critical difference with the newly proposed model is that the volatility process is a linear function of the level of the yield factors. We estimate our model using treasury yields data, monthly treasury yields data, and following the literature, we use eGauge11 as the measure of a model-free volatility. Some highlights of our empirical findings in the paper, we showed that the model implied conditional volatility performs well in capturing the model-free volatility, especially at longer maturities, such as 5 years and 10 years. The unconditional correlation can be as high as about 90% on average across maturities. And consistent with the literature, we showed that the two benchmark models do not perform well in capturing the time variation in the conditional yield volatility in our sample. And the performance of the two benchmark models in fitting volatility are actually very similar. Our models substantially outperform the two benchmarks in fitting yield volatility. For example, in terms of yield volatility root mean square error, the improvement of our model over the two benchmark model is about 33% on average across maturities. In terms of mean absolute percentage error, the improvement is about 40%. So these findings suggest that we can substantially improve the ability of the A-fine term structure models to fit yield volatility by modeling the volatility factor with a gauge process. And more importantly, in this paper, we showed that the improvement in fitting volatility does not come at the expense of a per fit of the level of yields. We show that the in-sample yield fit from the proposed model is very similar to those of the two benchmark stochastic volatility models. In addition, we also found that the proposed model can capture the empirical pattern in bound risk premium as characterized by the regression coefficient in the Camber-Shiller regression. So overall, our empirical analysis show that the proposed model can provide an adequate fit to both the means and variance of the yield curve. And this is mainly due to the different specification of the volatility factor. So now I'm gonna move on to discuss the structure of the proposed model in a little bit more details. So we propose a discrete time term structure model because the gauge literature is formulated in discrete time. We use standard three-factor model. The state variables are latent, follow a first order var process and both P and Q measure. Short rate is a linear function of the state variable. We consider a more parsimonious model in which the companion matrix are diagonal. And the conditional variance matrix is diagonal matrix with the diagonal element given by a gauge 1-1 process. To ensure the sigma square is positive, we restrict the parameters omega, beta, and alpha to be positive number. And the variance at time t+1 is no given information at time t, and also the initial variance. We're still gonna retain the tractability of the A-fine models. Based on Heston and Nandy 2003, we can derive the analytical solution for bound price, which is a linear function of state variables and the variance. The loadings are functions of Q parameters following a set of recursive relations. Given the bound pricing equation, we can easily write the continuous compounded yields. It's an A-fine function of the state variables and the variance factors as well. For conditional volatilities, we can extract them using the filter time series of the state variables and the estimated model parameters. So we derive the model implied 1 month conditional variance is given by this equation, where the last term is the variance of the pricing errors. So for the benchmark model, we follow exactly Diane Singleton's specification. The key difference is the modeling of the variance matrix. The diagonal term is given by a linear function of the state variables. And to ensure sigma square is positive, we follow those admissibility constraints as provided in Diane Singleton. Therefore, the benchmark models are different from our model in the parameterizations from both the state variables and the volatility process. So in order to compare with our proposed model, we also consider a restricted version and which we constrain the companion matrix to be diagonal. Therefore, the only difference will be the specification of the volatility process. But for both benchmark models, the key difference is the specification of the volatility process. In the benchmark model, volatility is a function of the levels, a linear function of the levels of the state variables. On the other side, for the newly proposed model, volatility is a function of lagged squared innovation. Let's move on to data and estimation. It's quite standard. We use monthly zero coupon bond yields with 8 different maturities, and we can write our model as a state space representation. We ask the model using maximum likelihood with a common filter. So for the empirical results, let me start by talking about the estimated parameters from the proposed model and the two benchmark models. So in this table, I present the parameter estimates for the proposed model, non-arbitrage gauge, and the canonical A13 model. We report the estimated parameters of the discretized VAR process for the benchmark model in order to compare with the estimates from the top panel. And we observe a few key differences in the parameter estimates. For example, the third factor is more mean reverting under the P dynamic for the benchmark model, but it reverses more quickly under the Q measures for the proposed model. And the volatility factor is quite persistent for the proposed model. For the benchmark model, we see that the level factor mainly affects the volatility of the slope of the yields. And beyond that, the second factor on the short rate is negative in the non-arbitrage gauge model, but it is positive in the benchmark canonical A13 model. So we get quite similar conclusion when I compare the estimates from our model to the other benchmark, the restricted version. We further examine the volatility like variance implied by this model. So by different model, that's the sigma square in the models. So in this figure, we plot the estimated sigma square implied by different model. For comparison, we also plot the eGarch11 estimated variance of 3 months yield, which is the right dotted line. And we can see the variance factor from our model, which is the blue solid line, has the highest unconditional correlation with the eGarch estimates. So now the question to ask is, what's the model's performance in fitting yield volatility? Here we plot the model implied 1 month conditional volatility, and together with eGarch11 estimates in the red color. The estimated conditional volatilities from the two benchmark models, the reddish purple color and the green color, are very similar, and they are much less variable than the eGarch estimates, as we see for all maturities that we use in our sample. On the other hand, the estimates from our model, the blue solid line, co-move closely with the eGarch estimates, especially at longer maturities, such as 4 years, 5 years, and 10 years. Our model fit the high volatility period. That's during the monetary policy experiment in the early 1980s very well for longer maturities. And our model does a better job in fitting the periods of low volatility from the mid of 1980s to 2000s. And beyond that, our model can capture the time variation at the beginning of our sample. So overall, this figure seems to suggest that our non-arbitrage gauge model can capture the time variation in the second moment of yields quite well, especially at longer maturity. So I have discussed those already in the previous figure. Now I'm gonna try to show you more evidence to assess the quality of the estimated conditional volatility. We check the unconditional correlations between eGarch estimates and the conditional volatility implied by different models. The estimated volatilities from the non-arbitrage gauge model have the highest correlation with the eGarch at all maturities. And on average, the correlation and conditional correlation is about 90%. On the next slide, we also examine the root mean square errors and mean absolute errors in the bottom panel between model implied and eGarch volatilities. And on the top rows of the panel A, we report the root mean square errors in basis point. And in the bottom two rows, we report improvement in percentage. So we can see the non-arbitrage gauge model outperforms both benchmarks in fitting yield volatility across all maturities and for both performance measures. So all those results show us that the non-arbitrage model performs better in capturing the time variability of the conditional volatility, despite we use only just a single volatility factor in the model. So a fair question to ask at this point is, how about the fit of the level of yields for the proposed model? So here we compare the model's ability to fit yields. In this table, we present the in-sample root mean square errors of yield fit in basis point. And from panel A, we got the results for all three stochastic volatility models considered in this paper. And we found that the improvement of the non-arbitrary gauge model in fitting conditional volatility does not come at the cost of fitting conditional mean of yields, because overall, across all maturities, the fits of the yields are very similar for those three stochastic volatility models. For comparison, we also present the fit for Gaussian model in panel B. We consider the canonical representation as in Jocelyn, Singleton, and Zhu 2011, which allows for a stable and tractable estimation of the Gaussian model. We estimate the maximum flexible form, and also we consider three restricted model. In all three restricted model, we consider a diagonal variance covariance matrix. In the second restricted model, we let the feedback matrix to have the same, similar specification as in A13 model, canonical A13 model. And in the last restricted form, we let the feedback matrix to be diagonal as in our proposed model. So it is not surprising to see that the maximum flexible Gaussian model has the best in-sample fit of yields. Overall, the Gaussian models outperform the models with time varying volatility for the purpose of fitting yields level. However, the Gaussian models are unable to capture the time variation of yield volatility. So these findings in particularly show that attention remains between matching yields and yield volatility in the proposed model. Okay, but when we compare to the Gaussian model in panel B, all models in panel A sacrifice the fitting of the cross-sectional fit of level to acquire flexibility in fitting conditional variance. So this is inevitable since in these non-Gaussian models, the state variables driving both the yields and the yield volatilities are the same and are spanned by the cross-section of the yields. But in these non-Gaussian models, we need the variance factors to be positive. The admissibility constraint in the canonical A13 model is more complicated, and which gonna create an asymmetry between fitting the first and second moment. However, the admissibility constraint in our model is much simpler. This is because we model the variance using a gauge specification. So this simpler constraint does not seem to result in a deterioration of the fit for the conditional mean of yields, as just shown on the previous table. So what we're trying to show in this paper is simply that it is possible for us to write down a parsimonious term structure model that allow for improved modeling of yield volatility as compared to the widely used benchmark in the literature, but without sacrificing the model's ability to fit the level of the yields. Beyond that, we try to provide additional evidence that our model can capture the time series property of the level of yields. So we conduct the Camber-Shiller regression analysis. We show that the proposed model can capture the empirical pattern in bound risk premium as characterized by the regression coefficient psi in the Camber-Shiller regression very well. So we run this regression using our sample and also the implied yields from different models that we investigated in this paper. We plot the regression coefficients for different maturities in the following figure. So from this figure, we can see, consistent with the literature, the Gaussian model, which is represented using this greenish blue dotted line with star, is exactly on top with the data, which is the red color in diamond line. And our model in the blue line with a cross is also get very close to the pattern that we observe in the data. But on the other hand, if we look at the standard stochastic volatility model, consistent with the literature, we show that they're not able to capture the deviation from the expectation hypothesis as we observe in the data. Okay, so overall, we try to show that our model can capture the time series properties of the yield level as well. Right, so for robustness in this paper, we check a few things. First, we try to estimate the model exclusively based on yield volatility. So the cross-sectional fit of the yield volatility will be the only objective in the estimation exercise. So therefore, it's gonna remove the tension in the models between fitting estimating the yield level and the yield volatility. And beyond that, we also check other measures of realized volatility, and we also check the performance of multiple volatility factors. So to give you a little bit more information on the robustness test, for the first one, like I just mentioned, we just estimate the model using a different objective function. The goal we are trying to achieve here is to remove the estimation tension built in the objective function. We find that our model continues to outperform the two benchmark models. And the second robust exercise we conducted is we check the another measure, a model frame measure. We follow the paper in the equity return literature, construct measures of monthly realized volatility using within months squared changes in yields. And we show that the two measures, this new measure and the EGARCH estimated, are highly correlated. Both measures show that our model continue to outperform the two benchmark models in terms of fitting yield volatility. So the results indicate that our finding, as I showed you before, are robust to the choice of the measure of model-free yield volatility. So another thing we investigate in the robustness exercise is we check the performance of the non-arbitrage GARCH models with multiple volatility factors. So in this paper, the main results is focused on non-arbitrage GARCH model with a single volatility factor. So when we estimate the model with 2 and 3 volatility factors, we find that the performance in fitting yield volatility is very similar to a single volatility factor model. So the first volatility factor plays a dominant role in fitting conditional yield. We showed that the third and the second variance factors also exhibit substantial time variation, but their magnitude is relatively small. We further conduct the likelihood ratio test, and the results indicate that there's no strong evidence that the models with 2 and 3 volatility factors fit the data better than the model with only 1 single volatility factor. So overall, that's what we have done so far for the robustness analysis. So to conclude, in this paper, we propose an affine term structure model in which volatility follow a GARCH process. This model combines the checked ability of the affine term structure models with improved modeling of yield volatility. And more importantly, in this paper, we show that the improvement does not come at the expense of a perfect of yield level. So our studies stress that the affine term structure model's ability in fitting yield volatility critically depends on the specification of the volatility process. So that's my presentation. Thank you for your attention, and I'm looking forward to the comments from my discussant.
Thank you so much, Rui. If you can stop sharing your screen, please. And so this, thank you. Discussant is Guillaume Roussellet from McGill University. Guillaume, the floor is yours. And your microphone is off.
Thank you. It's a pleasure for me to be here, pleasure for me to be discussing this very interesting paper about modeling volatility in term structure models. And having dealt with term structure models since the beginning of my PhD, I know this is a hard task to be achieving. So let me give you my perspective on this paper. All right, so let me try to summarize where the literature is at and what this paper does. In terms of, think about yourself as trying to design or, estimate one term structure model. And this is sort of a checkbox that you need to have whenever you're estimating those models. And so I group all the different things you want your model to have in terms of theory and empirics. In theory, you want closed form pricing. I'm going to focus on affine models today. So this is, all of them, they do that. Time varying volatility is something you have evidence for that, so you want to reproduce it. Zero low band consistency, maybe, maybe not. It really depends what you're essentially trying to achieve. And empirically, you want 5 different things. The fit of the yield levels, you kind of want to reproduce unconditional moments as well, mean volatility. You want to get a term premium, which is kind of plausible somehow. And this is not a given depending on the models. And you want plausibility of the volatility estimates, and this is what this paper is about. And the last thing that you might want to have is out-of-sample forecasts, which none of the models that are being considered and usually in the affine world do check. So I'm just putting this out there, but this is usually not very good. These models are not very good at forecasting. So you want to check all the boxes. First class of models, the standard Gaussian affine term structure model. Very nice early mid-90s model. Duffy and is the first paper to talk about that. It's in theory, you get closed form pricing. Of course, this is Gaussian. Don't get volatility either, neither ZLB consistency. It's got good fit. It's got good unconditional moments. It's got somewhat plausible premium. Volatility is out of the picture, so it's not there. People thought about this and said, well, why don't we use something like Cox and Ross models, or in discrete time autoregressive gamma models? In theory, these models do very well. They're usually positive. They produce positive yields, give you time varying volatility, closed form pricing. Empirically, they're a mess. Usually what's missing from there is the premium that you produce is completely implausible. The moments go all over the place. Volatility is not well reproduced either. And this is part of what Rui has shown in her presentation. You can also go to quadratic models. They seem to do a little bit better. Volatility is still kind of not there when you estimate these things, but they check more boxes. You can try to combine Gaussian factors with gamma volatility, and this is equivalent of the AMN models that constitute the benchmark of the current paper. You don't get zero low band consistency, but maybe you don't care about this. But still, the volatility plausibility is kind of not there either. So this is kind of an issue. And the last thing that I want to mention, maybe, this paper talks about state-of-the-art model that they want to be compared with. This is like the Wishart model. It's been barely used empirically because it's a mess to estimate. But if you're talking about some sort of like state-of-the-art model, this is somewhat in the picture. And because it's not being used, I put a bunch of question marks because, we don't really know how well it's doing systematically. Now, as you can see from this table, there's a key thing that's missing. Volatility plausibility is just not there for most of these models. And, the authors thought about it and say, well, it needs some solving. So the main question is, how can we model yield volatility a little bit more realistically in affine models? Before I just tell you a little bit more of what this paper does, having estimated a lot of dynamic term structure models in the past, this is pretty much how it feels. You're trying to make everything, all of this checklist sort of like checked, but every time you're checking more, one more of these features, then another one goes away, and it feels like it's trying to make everything fit in the box, and it's kind of complicated. So it's something I want to get out of the way first. All of the models I've been talking about, they're all misspecified. They don't do well out of sample. And this cheap shot is out of the picture. I'm just not going to talk about misspecification somehow. Okay, so now that this is said, what is the idea of the paper? The paper is model meets Heston-Nendy. What do you gain out of this? You preserve closed form pricing and time varying volatility. And then the authors show that you get some of the previous boxes that you wanted: fit, marginal moments, premium, plausibility. But on top of this, you get volatility, plausibility, which is kind of nice. Rui did a good job at presenting, what the mechanics are in the model. It's basically Gaussian VAR with heteroscedastic shocks. The heteroscedasticity is dealt with by Heston-Nendy independent dynamics component by component. And the main modeling result, if I had to summarize it, is that if you look at the moment sharing function of the yield levels and the volatilities, it's exponential affine. So all the closed formedness is going to be preserved. Proofs are kind of easy to do if you've been dealing with quadratic models. So everything's kind of neat. The main empirical results that they have is maybe best summarized by, well, not best summarized, but it's figure 1 of the paper. It's basically how their estimates compare with eGarch volatility that you estimate on yields. This is on the 3-month yield. Of course, the blue line is kind of doing better than the other two, which are doing extremely poorly. I would argue that this is maybe not the best picture to kind of like show the performance of your model. Maybe the 5-year is much better. At the 3-month maturity, there's a lot of other things that happen, like trying to reproduce all the different volatilities with one volatility factor is just very hard. So here, I would suggest that you replace this picture by the 5 years, which looks much better. But at the end of the day, the idea is just that the blue line does much better than the competitors. Okay, it's also easy to estimate through some sort of approximate Kalman filtering. Okay, so what are my comments? I really have one main comment about trying to know whether this paper is about specification or this paper is about estimation. And at the end of the day, I believe it's more about estimation. I'm going to try to argue this is the case. Then I have a bunch of suggestions for the authors to sort of like solve for this. I have a bunch of other comments, but I probably won't have enough time to talk about them. So I leave it to the authors and we can communicate on this afterwards. So, okay. The framework's nice. Everything seems to work pretty well compared to existing models. It's a natural sort of idea combining 2 different strains of literature. But the paper claims that the superiority that they get is due to the physical dynamics, that the specification is somewhat better. If that's true, and this is where what I talked about, and that can only be checked with some sort of like forecast or out of sample forecast. It's easy to get fit in a model where you have as many factors as you want, but actually forecasting better is a hard task. And the claim that they have is based mostly on the fact that the fit is similar for the yield levels, but the variance series are actually better. And so my question is, could the estimation method also kind of be part of the equation, namely the Kalman filter? And this is based on my own sort of experience estimating these models and my own intuition. So what seems to be happening to me is the following. Think about the Kalman filter as some sort of like method of moments that's going to try to maximize the fit on the mean and on the variance of yields. Essentially, that's to me, that's what's going on in terms of time series. Now, factoring the fact that yields are extremely persistent and yet stationary, and this is kind of a hard problem in terms of estimation. So what does this mean for the Kalman filter? The Kalman filter sees this and it's like, well, I have a very high penalty if I don't fit the yields as much as I can. So it's going to try to reproduce the time series of the yields themselves. And then if you're lucky, or if the Kalman filter feels like you're nice, it's going to try to also do a little bit of things on the variance. But the variance definitely comes second. The key message here is that the Kalman filter always favor the fit of yield levels and up to the overfitting, basically. So what happens in 3 different models? First, consider a gamma model. Variance of yields are linearly related, and it's just super tight link between the 2. What does the Kalman filter do? It says, well, variance, I don't care about this anymore. I just want to fit yield levels. And so your variance of yields looks like the level of yields, period. So you fail. For a Gaussian model with gamma volatility factors, now you're on the other side of the spectrum where mean and variance are completely independent, but variance is still part, because it's priced, it's still part of the yield levels. And so the Kalman filter can choose to use what you call variance factor, either for the variance of the other factors or for fitting yield levels. And it's going to choose the latter. It's choosing your vol factors to fit yield levels. So it's not really a volatility factor anymore. Now, what I'm suspecting is happening for that model, the GARCH with the Gaussian model with Hest and Nandy, is just you're sort of like in the middle. You're kind of imposing that this link between yield level and yields variance is very specific through not only the lag, but also the square of the lagged innovation. And so that's, to me, that's just the right level of tightness that's kind of going to be correcting the weight that the Kalman filter imposes on the mean and on the variance. And because you got the lag in there, the Kalman filter cannot do whatever it wants with the GARCH estimates anymore. And that's kind of helping it somehow to pin down the volatility better. Now, you think about this and you say, well, but they have a robustness section that just asks how these models are doing when you're estimating them on volatility alone. And this is where I'm kind of failing to really understand the procedure that the authors have, because we did, in a previous paper of mine and my co-authors, we conducted such an experiment. This was on Japanese data with a pure gamma model, and we sort of imposed into the Kalman filter that volatility series should be well fitted. And this is what we get essentially, this graph. So this is the 2-year yield and the 10-year yield volatilities. And you see that, you know, we can actually do it and pretty well. So I'm not sure exactly why in the paper this sort of experiment fails for standard Gaussian gamma factor models. And so my question is it just that you gain superiority because the Kalman filter really favors the first moment and you don't give the Kalman filter any information whatsoever about the second moment more than the specification? So I know that I still have, what, 2 minutes? So suggesting to sort of like convince me. If you really want to fit volatility for any of these models, then provide information to the filter to fit volatility. All the models are fine. The GARCH model, the ATSMs, the different ones that we've seen. So you can actually ask the Kalman filter to fit those eGARCH series that you have, and then do a fair comparison of all the different models. Now, another way to do this would be, well, try to filter, try to price also interest rate options or swaptions, which are quasi-closed form. But that's naturally going to pin down the Q volatility, and then you're going to be able to deduce the P. And so Jocelyn and Konchitsky, they have a recent paper in JFE saying, well, if you're trying to do that, A14 is actually all you need. And so that's, you know, that's hard to reconcile with the author's finding here. Maybe just variance, maybe, you know, think about other types of securities that could guide you to get some sort of variance estimates, but something could be done there. Volatility specification, there's this very nice paper by Cécile Sarisoy that's providing you also the theoretical statistical framework to do that. Otherwise, if you decide to go another route, then I think the case is harder to make. You're gonna have to show out of simple forecast simulations, anything like edging properties, cumulative returns of different strategies. It's a really hard case to make. So I would suggest staying in the world of in-sample fitting. I think I have 1 minute maybe, Pascal. My other comments very briefly are about technicalities, I think. The first, I'm just gonna briefly mention them, not really detail the slides here. The first comment is really, I have some issues with the Kalman filter algorithm and the way it's sort of like designed. And so I suggest here another way that I feel is more natural. But maybe a deeper point is, you know, Kalman filter empirically is a little bit hard. The likelihood is not well behaved. It's kind of complex to estimate models with Kalman filter. And it goes against sort of the idea that GARCH were preferred to stochastic volatility model, namely because they were supposed to make you avoid filtering, which was kind of a nice feature of GARCH models. So here's my suggestion also in terms of estimation. Maybe consider just under the Q measure, which allows you to get PCAs, basically. Treat these PCAs as observed as the 3 factors that you need to price the term structure. And then under the P measure, think about these PCAs as having volatility, so an unspanned volatility model. And now, because these PCAs are essentially observed, you can estimate recursively through standard QML your volatility mole, and it's not going to be such a bother as the Kalman filter was. And if you're interested in that, your pricing kernel that produces this sort of like unspanning is exponential quadratic, so you still get a lot of close formedness in there if you're interested in that. I have a bunch of other comments about generalization. Interruption seems to be hard to do in the framework, but I'm not going to talk about this. These are a bunch of minor comments, and that's pretty much it. So thank you very much for allowing me to discuss that paper. Very interesting paper. Again, I think the idea is neat, but if the authors can clarify the few points, it'd be great. Thank you.
Thank you, Guillaume. Rui, you want to respond?
Yes. First, thank you so much for all the comments. I think they are very helpful for us to improve our paper. So I think one point being raised in our discussion is related to one of our robustness exercise. We try to use the cross-sectional fit of yield volatility as the only objective in the estimation exercise. So we simply minimize the sum square errors of the yield volatility. So we're doing this because we try to remove the tension between fitting level and volatility in the objective function. But you are right, we do not observe that the performance of the benchmark model in fitting yield volatility got improved a lot by doing this. So I think you bring up a very good point. It could be due to that the Kalman filter still plays a more weight on the first moment in the estimation. So it's interesting to see if more information is provided to the filter process to fit volatility, what's gonna happen. So, but in order to do that, we probably need to maybe extend our model to the pricing of like swap options or other interest rate options. So maybe my intuition on this is that it may help us to have the benchmark model to pen down the volatility process when adding like more information in the estimation. So, but at this moment, we didn't change any other things. We still use the yield curve information. We just simply change the likelihood to sum square errors of yield volatility in the estimation. So I agree there could be another approach for us to improve the modeling of the conditional volatility by adding such as like more information. But what we're trying to show in that exercise is, so even though we remove the tension in the objective function, still modeling volatility as the level of yields is not that helpful to capture the second moment of yields. So that's what we're trying to show in that exercise. And another thing I want to make a clarification on is the one equation in the appendix that you mentioned about the Kalman filter algorithm. That's a pretty good catch, and thank you for very careful reading of our paper. So we did use the constant alpha like in the Kalman filter algorithm when we project the variance. It's just the way we write the one equation before that, I think it caused the confusion. But thank you for bringing this up. We will definitely clarify that in the paper. And another point I think it may deserve some more investigation is that you suggest that maybe we can separate the P and Q measures, and therefore we're gonna have a unspanned volatility. And by doing that, we can use the principal components as the factors. And in this way, we can avoid the Kalman filter in the estimation. The Q parameters will be estimated through maybe certain normalization using cross-sectional information only, and the P parameters, including the gauge, can be estimated through likelihood on the observables directly. So we haven't tried that yet, but we think it definitely deserves more investigation. But my intuition on that is currently we're using latent factors and Kalman filter in the estimation rather than observable, because it is still a question whether the factors can fit yields well are the same as the factors that can fit volatility well. But it's an interesting point. This is something we're gonna check like in our future work. And another thing I think you just briefly mentioned, but I think it's good to talk about it as well. So you try to generalize our model to consider the covariance in the variance covariance matrix. So at this moment, we just model the variance using the Gauge process because we try to keep our model as close to the Diane-Singleton specification in which the variance covariance matrix is diagonal. So we want to show that the improved performance is by the specification of the variance factor only. So that's why at this moment we keep with within a more parsimonious model. But it would be interesting to check if we could generalize a variance covariance matrix in our modeling in the future work. So I think overall all the comments are very helpful. Thank you again for the great discussion. We will try to incorporate your comments in the revision of the paper. Thank you.
Thank you, Rui. Now I can open a period of questions from the audience. There's nothing on the chat box for now, but has anyone has a question for Rui? Well, maybe I can start by asking one, but just a simple question by curiosity. Can you say something about the difference in fitting performance between the first 10 years of your sample, where the yields have high level and high volatility, and the last 10 years, where the yields are relatively low and the zero level boundary is a real concern?
Yes, I think in terms of fits of volatility, our model Gauge in particularly can catch the specs very well in the 1980s compared to the benchmark model. The benchmark model thinks it specifies the volatility as a linear function of state variables. It can catch the moment a little bit, but it's not able to capture the spike. And also we show that in our paper for the low volatility period, it seems like the benchmark model always overestimate the low volatility time period. So our model, especially at long term, will able to provide a much better fit at the low volatility period as well. So that's what we observe from the empirical analysis.
Okay, thanks. Liuren has written a comment. It's pretty long, so I'm not sure I want to read it. Maybe Liuren, you want to ask a question by yourself? Or maybe not.
Pascal, this is Chris. If there's no more questions, can I briefly respond to something Guillaume said?
Yeah, sure. But briefly, right? We have a couple of minutes. Thanks.
Yeah, so thank you, Guillaume, for your excellent discussion. I really like what you said about the Kalman filter and the role that plays, and we have to think about that. But so let me pick up on what you said towards the end, which is that why don't you just take basically the three first principle components, and then basically you can get rid of the Kalman filter. Now, of course, the reason we don't do that is because we have a benchmark where we need something like the Kalman filter. So we sort of wanted to sort of compare apples and apples. But now that I think of it, you're absolutely right. And we should, after we do that comparison with the standard A13 model, we should repeat the exercise with the first three principal components. And then that might also answer some of your questions about the role that the Kalman filter plays. So that's an excellent suggestion that we definitely are going to implement. Thank you.
If I may, it's also okay, so choosing the AMN model is also one way of seeing this, but if you go directly to discrete time and you have a Gaussian model where you have basically gamma volatility factors, that might be another benchmark that you can consider, and estimation could be performed in a similar fashion. Now you got to use the Kalman filter just because it's a stochastic volatility model, but gamma factors, they have their own limitations as well, and so you might be able just to beat them just because of the specification and not of the estimation. But this is something that you got to see empirically, I guess.
Thank you.
Okay, thank you everyone. We need to move on